Hey everyone, it's JD. I got asked to see if I could come up with an easy way to understand volume of distribution, and so I'm gonna make this quick video, I guess, and if it's helpful for you, great. If not, I'm sorry, but anyways, I'm gonna explain it two different ways. One is the way that I understand it conceptually, and then the other is the way that I understand it mathematically. And so first, conceptually, these two, we're going to say this first up here, this is, ooh, that's a large, let's say that this is your total volume of blood in your body, right? And we're just going to, I'm just making these numbers up just to make them easy, but let's say that we have 10 liters of blood, right? So we have 10 liters of blood, and then we're going to inject some drug. So I'm going to say we're going to have 10 units of blood. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 units of blood, 10 units of drug in 10 liters of blood. Now, after some time, a bunch of this drug, we're going to say 8 of these units of drug are going to leave the blood. So they're going to leave the blood and go into tissues. So all of these would be leaving, right? Now, so what we're left with in the blood here is 2. Sorry, this guy is still there. Right? So we're left with 2 here. Now, I know that I put in 10. I put in 10 drug. And we're leaving a lot of units out of here and everything, and the reason is because we don't want to confound things. We'll add units whenever we do things mathematically. But now, if I look at, let's see, if I look at this is like at some time down the road, after some time waiting, I would look and say, well, my concentration in this blood is really, really low right now, right? But I already know that I put in 10. So the only way that I can figure out my 10, the only way I can get to my 10 is to say, well, there must be more blood there, or there must be a larger distribution. 1, 2, 3, 4, 5, 6, 7, 8, right? So if the concentration of the drug that we have put in at a known amount goes way down here, well, then we must think that it's being distributed over a much larger area. So my apparent distribution now is 5 times larger than what it was when I put it in. So what that shows is that this drug must have left the vascular compartment and went somewhere else, because it appears that it's distributed over a much larger area or a much larger volume than what it really is. In fact, 5 times larger. So that's how I understand this conceptually. Okay, so now how do we understand this mathematically? So let's just erase all this. We're going to leave that up there, and we're going to say that's still blood, and we still have 10 units of drug, except for now we're going to say that it is 10 milligrams of drug that we put in. So 10 milligrams drug injected. Now, we're still going to have, well, actually, let's say volume of distribution, and we're going to go with the formula. So the volume of distribution is the mass of the drug over the concentration of the drug. So mass of drug over the concentration of the drug. Now in this case, we put in 10 milligrams of drug, 10 milligrams of drug, and the concentration of the drug is 10 milligrams per 10 liters, because we have right here 10 liters of blood. So now if we do this math, in order to get this out to liters, we're going to go 10 milligrams on top times the reciprocal. So we're going to have 10 liters over 10 milligrams. And then we're going to do some unit canceling. We cross these out, right? So now we have 10 over 10 on, or 10 times 10 on top. So we have 100 liters over 10, which is going to equal 10 liters. So our apparent distribution is exactly the same as our actual distribution, because it appears that the drug is distributed over 10 liters, and in fact, our blood compartment that we designed here is 10 liters. So that means none of the drug left the vascular compartment. All of it's still in the blood. All right, so now let's look, and we're going to go ahead and move those out just like we did. We're going to say that 8 milligrams of the drug left the vascular compartment and went to tissue. So this guy left, this guy left, this guy left, this guy left, this guy left. In fact, let's just do 5. This way we can do this a couple of times. So let's say that 50% of the drug left. So we are left with 5 units, 5 milligrams in that same 10 liters of blood. Okay, so 5 milligrams in that same 10 liter of blood. Now let's do the math. The volume of distribution of the drug is equal to the mass of the drug over the concentration of the drug. We're going to do the same thing. How much drug did we put in? We put in 10 milligrams. We still put in the 10 milligrams. It's just left the vascular compartment. Now the concentration of the blood is no longer this 10 milligrams per 10 liters, but it is now 5 milligrams because 50% of it left. So now it's 5 milligrams per that same 10 liters. Okay, so now we do the algebra, and we say 10 milligrams over 1 multiplied by 10 liters over 5 milligrams. All right, so we do some canceling. Milligrams cancel, right? Now we have 100 liters over 5, just 5, because milligrams is gone. Oops. And where did we go? There we are, sorry. And we're left with now 20 liters for our apparent volume of distribution. Okay, so it's higher than the amount of blood that we actually have, right? Okay, now let's go one more, and let's say 8 leaves. So we're gonna wait a little longer here, and let's do 9. All except for 1 leave. So now we have volume of distribution. Just do it over here. So the volume of distribution has to equal the mass of the drug over the concentration of the drug. And we put in 10 milligrams. Now we only have 1 milligram left per that 10 liters. And so now we do the math. We've got 10 milligrams over 1 multiplied by 10 liters over milligram. Our milligrams cancel. we now have an apparent distribution of 100 liters, right? So what we're seeing is that the more drug that leaves the vascular compartment, the higher the theoretical apparent volume of distribution is. So what we can do is use that. We can say that when we do calculations, if we come out with a number, after taking a sample, we come out with a number that the apparent volume of distribution is equivalent to the known, the amount that we put in over the concentration, then if it comes out to be the same, the measured amount versus the theoretical amount, we know that nothing of the drug has actually left the blood. It's all still there in the blood. And the higher the number goes, the more drug must have left. If all the drug left, right? If all the drug left, your apparent volume of distribution would be infinite, right? You would have infinite distribution because your concentration is essentially nil at that point. Okay, so what we can then do that is we could compare two drugs, right? We have drug X and drug Y. And if at time 0 we give 1,000 milligrams of drug X and 1,000 milligrams of drug Y, and we use whatever volume of blood we want to use or whatever. There's a standard amount. I forget what it is, 40 or something. How many? Let me Google it. How many liters of blood in the water in the human body? Wait, it's not 40. It's 42 like total, right? So there's 5 liters. So whatever, we have 5 liters. So let's say we have 5 liters here. And don't use this exact amount when you're calculating because there is a number that we're supposed to use and I just don't remember what it is. But it is standard, and then the standard weight is going to be 70 kilograms for the standard male patient. Now what we can do though is we can look at this and we can say that at time zero, they're both going to have the same concentration, but at time t, if drug X has a very high volume of distribution, and at time t, if drug Y has the same or a lower volume of distribution, we're just going to say that it's lower in relation to drug X, not in relation to its initial, but it has a lower volume of distribution, then drug X must have left the vascular space more readily than drug Y did. So that's my understanding of it. Hopefully that's correct.